You must already have heard about the twin primes. So the primes, they can also be twins, and twin primes are the numbers which differ by 2. Like you have the numbers say 11 and 13. So you can see they are consecutive odd numbers and they both of them are prime and they differ by 2. Can you name some more pairs of such prime numbers which differ by 2? We have 17 and 19. This is also a pair of twin primes. And likewise, if you proceed further, then 21, 23, 25, 27, 29, 31. 29 and 31, this is yet another pair. And likewise, if you carry on finding so many, you will find so many different pairs of twin prime numbers. So very common concept, and I think most of the school students, they study this the twin prime numbers. Likewise, you have the term co-prime numbers. So the co-prime numbers are the numbers whose highest common factor is 1. So these numbers are often confused with prime numbers, but they may not be prime. Like if I take an example of say 8 and 15, both of them are not prime because 8 is divisible by 2 and 15 is divisible by 3, 5 and so on. And so they are not prime. But if we consider both of them, the highest common factor between 8 and 15 is 1, because 8 is divisible by 2 only, so 2 times 2 times 2, and 15 is divisible by 3 and 5. So there is no common factor between them. So the highest common factor of 8 and 15 is 1, and therefore this pair of numbers is known as a co-prime pair of numbers. So you should avoid that confusion. Co-prime numbers are not prime numbers. They have no common factor. That means the highest common factor is just 1. So that is one more amazing thing about primes. Then next up we have a strange name here, Mersenne primes. If you see this name, I may be pronouncing it wrongly, but you can check on Google. What are Mersenne primes? Now again, it has to obey some property, right? And Mersenne primes also obey one such property. So any prime number of the form 2 raised to power p minus 1, any prime number which is in this form 2 raised to power p minus 1, where this number p is also prime, p is also prime, is called a Mersenne prime. Like let's take an example. If I take p as 2, so 2 square minus 1, how much will that be? 4 minus 1, 3, and 3 is again a prime number. So here also you should have a prime number, and when you calculate this, you should get a prime number as the answer. Likewise, you can take so many different examples of Mersenne primes. If you put 3, 3 is also a prime number, right? And 2 cube is 8, 8 minus 1 is 7, and 7 is also a prime number. So 3, 7, all these are Mersenne primes. You can take 5 also, like 2 raised to power 5, 32 minus 1. So 31 is also Mersenne prime. You can try so many different things. See, 2, 3, 5, they are consecutive primes and everything is getting me a Mersenne prime. But it doesn't mean that every number will give me a Mersenne prime number. So you can try, experiment this, and I'm sure you are going to be amazed, by the results which you will get. Then we have something called Sophie-Germain numbers. So these are Sophie-Germain primes. So another different property, another different name given to the prime numbers. So what is the property which is to be obeyed here? Now we need a prime p such that 2p plus 1 is also prime. Any prime number which can be written in the form 2p plus 1 and where p is also a prime number, that is called a Sophie-Germain prime. Now what's the example? Let's take the example of 23. How do we write 23 in this form? It is 2 times 11, 22 plus 1. See, this 11 is a prime number, and when you put 11 in 2p plus 1, it is getting me another prime number, right? So this 11 is called a Sophie-Germain prime. Likewise, you can try some more combinations. I think 53 also works here. If I take 53 here, I will get this is 106 plus 107, and 107 is again a prime number. So you can go on and try some more combinations. I think 41 also works. If you see, 41 is 2 times 41 plus 1 is 82 plus 1, 83, which is again prime number. So all these numbers which I am writing in the bracket, no, they are Sophie-Germain primes. Likewise, very related to this concept is the concept of the safe primes. Safe primes. Now, how do you actually define these safe primes? Is how you define Sophie-Germain primes. So this is the prime number, right? And here we have the Sophie-Germain prime. The other side, this will be a safe prime. So if you want to define it, it will be a prime number p, where p, this is p, right? So p minus 1 upon 2 will also be prime. P such that p minus 1 upon 2, this is also a prime number. Then we will call p as a safe prime. Now there are a lot of things to understand, a lot of things to enjoy. When you start getting into a topic, you realize there are so many different angles and so many different concepts which we still don't know. Most of the students, most of the people who are preparing for competitive exams, they just know that prime numbers are the numbers which have only 2 factors, the 1 and the number itself. And they know a series of prime numbers, 2, 3, 5, 7, 11, 13 and so on. At most, what they study is, they know that okay, the prime numbers follow some definite patterns, and what are the various prime numbers less than 50, or some of them will know numbers less than 100 also, right? That's it. But it's a big topic actually, and there are so many different concepts which we are still unaware of. So let's take another one now. This is really important. This is a very important property of prime numbers, and I'll try to prove it in front of you in this video. Okay. So the property states that whenever you have a prime number p, suppose p is a prime number, then p square, the square of the prime number reduced by 1, this will always be divisible by, is always divisible by 24. Now I am going to prove this. Why square of a prime number minus 1 is always divisible by 24, or it is a multiple of 24. So for understanding this, let's try and factorize this p square minus 1. So we all know that p square minus 1 can be factorized as p square minus 1 square, that is p plus 1 and p minus 1, right? So there are 2 factors. Remember, p is a prime number here. Okay. Now first thing I am going to do is to plot it on a number line maybe. So this is p, this is 1 less than p, p minus 1, and this is 1 more than p, p plus 1. Now we know that except 2, which is the smallest prime number, and it's the only even number which is prime, this p is not even, right? It is not even. So 4, 6, 8, 10, they cannot be even because they are all divisible by 2. Now when this number is not even, that means it is odd. 1 less than the odd number is going to be even, and 1 more than the odd number is also going to be even. So p minus 1 and p plus 1 actually are consecutive even numbers. And whenever you have 2 consecutive even numbers, if one of them is divisible only by 2, then the next one will be divisible by 4, right? Just think, you have number 12 and 14. See, this is divisible by 4 and this is divisible by 2. You take any other pair, say 30 and 32. 30 is divisible by 2 but not by 4, but this is divisible by 4. So consecutive even numbers, if one of them is divisible by 2, then the other one will be divisible by 4. Correct? Now, out of p minus 1, if I assume that p minus 1 is divisible by 2, it can be the other way around also. If this is divisible by 4, then this will be divisible by 2. Okay? So you can take both cases, it works both ways. So if p minus 1 is divisible by 2, then this one, p plus 1, will be divisible by 4. Correct? And from these two, what will happen if I multiply these? P minus 1 into p plus 1. It will be multiplied, it will be a multiple of rather 2 times 4, 8. So it is divisible by 8. Does that work? And does that make sense? Just take some examples and you will understand why p minus 1 into p plus 1 is always divisible by 8. And therefore, this product is obtained from this, right? So, p square minus 1 is actually divisible by 8. So, 8 times something, right? Now, this is the first thing I wanted to obtain. Now, let's do the same thing again. I will plot it on the number line here. P minus 1, p plus 1. Right. Apart from the number 3, which is the smallest multiple of 3, which is a prime number, right? This p is not divisible by 3. Not divisible by 3 because it's a prime number, right? Not divisible by 3. Just think, if a number is not divisible by 3, its predecessor or successor, one of them will surely be divisible by 3. Can you take an example? Let's try not divisible by 3. So let's take 10. Prior to this we have 9 and after this we have 11. See, 9 is divisible by 3. If you take a number like say 20, then 19 and 21. Now see, 19 is not divisible by 3 but 21 is divisible by 3. So one of the numbers, the predecessor or the successor, will always be divisible by 3. Right? So either p minus 1 or p plus 1 will be divisible by 3. And so even if one of them is divisible by 3, their product p minus 1 times p plus 1 will be divisible by 3. Correct? And so p square minus 1 is 3 times something. Right? It is divisible by 3. Now look at the two results which I got here. I got p square minus 1 is 8 times something and p square minus 1 is 3 times something. So obviously if something is divisible by 8 and 3 both, then p square minus 1 is actually divisible by 8 times 3, 24. And therefore p square minus 1 is always a multiple of 24. So everything has a logic. You can see I have taken two cases. In first case I proved that p square minus 1 is a multiple of 8, and in the second case I proved that p square minus 1 is a multiple of 3, and so it is a multiple of 24. So any prime number, if you square that up and subtract 1 from it, it will always lie in the table of 24. Can you take an example? Let's take p as 11. If p is 11, then what is p square minus 1? It is 11 square minus 1, that is 121 minus 1, 120, and that is 24 times 5. So it is divisible by 24. So friends, the numbers are amazing. You keep on getting into a particular concept, and you will find that the knowledge is endless, and you keep on doing it, keep on researching, you get new things, and that's what makes mathematics so beautiful. So friends,